Okay, so let me actually start with the main part of the talk and explain these notions that we have just heard about in the elevator pitch. So I kept talking about boundary of the opera plane. What is that? So here we see this colorful picture which depicts the opera plane. So this line is, if you want, the real line, right? This boundary here, and the colorful tessellation we're showing the tessellation by fundamental domains of the modular group SO2Z, which acts on the opera plane in the familiar way. I'll just write it down explicitly for the sake of setting the notation. Okay, so what we call gamma tau is just this familiar transformation here. Okay, and then the boundary, well, obviously it has one boundary, which is the point at I infinity. However, I infinity gets mapped to other points, namely the totality of the rationals by SO2Z. Okay, so it's more than natural to include all the rationals inside in the boundary. So in fact, SO2Z modular group acts transitively on this set. So every point can be mapped to any other point. Okay, in this set. So this is what we call the cusps, and they constitute what I call the boundary of the opera plane. And these cusps correspond in different contexts to different things. For instance, they correspond in the context of 2D lattices to degenerate lattices. And relatedly to the degenerate limit of an elliptic curve and low temperature limits in the physics application, etc. And the behavior near the cusps, or what I call the boundary condition of in the context of a modular form, then determines the growth of its Fourier coefficients, as for instance, we have heard about in Sergey's talk, and that's known in the physics language as Clarity formula, or more precise version, the Rademacher sums or Poincare series in the context of analytic number theory. So we're interested in taking the limits to the boundary. Okay, so we have a point in the opera plane, and we want to, approach a point, a cusp or a rational point vertically like this. And what that corresponds to in the usual exponential map between a point on the opera plane and the unit circle is that we're taking the so-called radial limit by approaching a root of unity. Okay, that we have also heard a lot about today. And so for a function on the opera plane, so with now I'm just making things more precise with the boundary condition that it's finite at all costs. As t goes to for all x, then what we can do is that we can define a function on the opera plane. I'll call it, on the rationals, I'll call the f check by just taking the radial limit of the original function on the opera plane, right? So in this way, from a function defined on the opera plane, I naturally get a function that is defined on the rationals. So what kind of properties does this function have? This function on the rationals. It depends, of course, crucially on the properties of the original function. So if f is a modular form, Well, we all know what it is, but just for the sake of setting notations, it is a holomorphic function on the upper half plane that satisfies the condition that, the transformation given by the something called weight, namely this W, which gets translated into this weight function. Weight factor in the transformation is the same as the original function, then it's called modular. Okay, then of course you need to have all the invariants for all the elements of a group gamma, well, which we will take to be a subgroup of the usual modular group SO2Z. Okay, then the ensuing function defined on the rationals satisfy this property. Namely, if we take the modular difference, I apologize for the little typo. Now we're on the rationals, okay? So this cocycle of f check, namely the function itself minus its modular transformation, vanishes. Okay, that arises just from the modularity transformation of the parent function. All right, so and it has to hold for all rationals apart from the points that will get you to I infinity and for all gamma. Okay. So from a modular form, the function we derive on the upper half plane, this f check, will have the property that the cocycle vanishes. That's just a natural translation of the original modular property. So we'll also consider something that's, also modular, but no longer satisfy the condition that they're bounded at the boundary. So we consider something that blows up at the boundary, which is the so-called weakly holomorphic modular form. So a famous example is the J function, okay, which is invariant under the whole modular group, and which has this Fourier expansion near q equals 0 or I infinity. Okay, so we could see explicitly the behavior at q at the cusp that it has, let's say, bad boundary condition, that now it has a singular behavior near the cusp. Okay, that's why it's only called weakly holomorphic. And it is optimal in some sense. In what sense? If you want a function that is invariant under the whole SO2Z and you want it to be non-trivial, then basically this is the unique example that that has this minimal, if you want, minimal singularity at the cusp. If you let the singularity to be worse, for instance, when it starts with like q to the -2 power, then you have more choices. But this is the, the mildest behavior you can have in order to have a non-trivial example modular function on the upper plane. So, okay, that's optimal. And another property that's famous about this function is that these numbers, 1, 9, 6, and all these integers, they are, also the number of the dimensions of a certain module or representation of the monster group. Okay, so this is the famous monsters moonshine behavior story, that this is a module. These are all modules of, you know, the monster finite simple group, which is the largest of all sporadics. Okay, so that's very nice. So we have an optimal function in its limiting behavior, and it encodes, you know, a very nice representation for the very nice and interesting finite simple groups. So now, well, as we said, this property is very nice, but it just means modularity. And then what's the more general, let's say, behavior for a function near the cusps? Okay, so another nice set of examples are provided by Ramanujan. And he wrote down a bunch of, you know, functions in the form of some Q-hyper geometric series or Eulerian series, if you wish. So one concrete example looks like this, okay? So it's very, very concrete. You just take it and then take this formula, and then you can expand it to, you know, as many powers as you want. And for instance, if I just expand the first few like this, and then I'll have such, you know, expansion. So, well, a few things we can already observe. The first is that it's also singular at the cusps. For instance, at I infinity, you can just observe, because I put in this negative powers of Q already. And for other cusps, you can also, you know, do a little numerical investigation, and then you will see that indeed it blows up. And also that it has nice integral coefficients. And third, just like the J function, or even better, it has very slow growth and in its Fourier coefficients. Well, actually, after the fifth power, you will see like non-trivial coefficient. Not everything is one, but it grows slowly. So, like Ramanujan was also very interested in the behavior of such functions near the cusps. So yes, given an Eulerian series, such as this one, is there a modular form such that the difference between the two is of order 1 at all cusps? Okay, so he asked basically, like, this is not a modular form, but can it at least have the same behavior of as a particular modular form at all cusps? And the answer is, he said, is not necessarily. He then stated that when it's not, I call the function a Mach theta function. So actually, this not necessarily he didn't prove, and it was only proven recently by 3 mathematicians, which says that indeed that if f is one of the Mach theta functions of Ramanujan, then there is no weakly holomorphic modular form f prime such that the difference is finite at all costs. So exactly what Ramanujan stated. So how can we go about improving such a thing? Well, it actually relies on the modern definition of Mach modular form, which we have heard already. But just for the sake of notation, let me actually briefly just repeat that. So a Mach modular form is, again, a holomorphic function on the upper half plane. And I'll use the abbreviation MMF. Oh, sorry, my tablet is acting up a little bit, but I say this is a MMF, modular form, if there exists a modular form G such that if we define G star to be what's called a non-holomorphic Eichler integral. So as the name suggests, it's a non-holomorphic integral. And if we define such a thing, tau prime, and we subtract this function from the holomorphic function, then f behaves like a modular form. Okay, so if you can find such a G, such a modular form G, which we call the shadow of F, such that we can correct the non-modularity of F, then we say it's a Mach modular form. And using this, combining the previous results in this definition, we can actually show that there is a set of cardinality larger than 1 such that f minus f prime j of x is O1 at all cusps x. Okay, so what does that mean? It means that we have shown, as Ramanujan said, and as the three mathematicians have proven, there does not exist one single weakly holomorphic Mach modular form that can cut out all the singularities of Mach theta functions, but you can find a finite set, okay, such that for each cusp you can use one of these elements to cut out the singularity. Okay, so that's the definition, and hence mimicking the case in the case of modular form, we can define again a function on the rationals by taking the limiting value, okay, of the difference. All right. So also from Mach forms, we can derive such a function. So now maybe we want to know, like, what are the other Mach modular forms, like F0, which means that it has integral coefficients and it has very slow growth. Okay.
I've got a question.
Yeah.
The previous slide.
Yeah.
Shouldn't you add the shadow to the Mach modular form?
Well, then I can just change G to minus G.
Yeah. Okay. Yeah. Okay, that's the
so minus G is also a modular form, so it doesn't matter. It's just slightly more convenient for what I do.
Okay.
Yeah. Okay, so that's very nice. And now I want to ask the question, what are the other Mach modular forms that have integral coefficients with slow growth? Okay, so for that, I need to define what's called the Mach theta function. And then, so let me briefly introduce this function with two variables. So not just tau, but also with a Jacobi variable, okay? And it just looks like the usual theta function because it is what it is, okay? And we all know that such functions have Jacobi-like properties. And from it, I can define, well, two functions that that's defined on the upper half plane. So I will be either 0 or 1. That's where this two function comes from. So what I do is that I take the dz derivative, okay, if necessary, of this Jacobi theta, and then I put the Jacobi variable to 0. Okay, with this setup. And now I want to consider the so-called Mach Jacobi forms, which mimics the usual Jacobi forms. And I'll first start with weight 1, since that's where we encounter Ramanujan's function. So what are they? They're basically the same as a vector valued Mach modular form, such that there's a vector valued, so a vector of modular forms, which are the shadows. And then, of course, then that will lead to a vector of completions. Okay, so R is such that, when we combine these completions with the theta function with 2 variables, so this is not 2, this is my z, I apologize, then it transforms just like a usual Jacobi form. Okay, good. So we want to find Jacobi forms, Mach Jacobi forms that leads to Mach modulus forms with these 2 properties. Okay, so we all know that slow growth, meaning that the behavior near the cusps have to be mild. So we might want to require that this is bounded again at all cusps, okay, when we take the limit. However, you can actually show that there is no solution to this problem. This is a bit too stringent. So what you can do is to, to go for the second best, and this is the second best, namely you multiply with some power of Q, for instance, such that it's sufficient to kill all the singularities at the cusp I infinity, and it turns out that there are solutions. So this is a good property, and we will call such thing an optimal Mach Jacobi form, drawing in inspiration from the optimality of the J function. And so you can consider such a definition for all positive integer m. So in particular, it's not for a priori clear, okay, whether you will have finite answers. Okay, so what we have proven are 2 things. The first thing is, okay, you want integer coefficients. Fine. So what that translates into is that G, the shadow, or the shadow, are in fact theta functions. Okay, not some funky cusp forms or anything, they're just theta functions. Otherwise, you're bound to have, terrible transcendental coefficients, which cannot count any BPS states. And the second is that there are precisely 39 such optimal Mach Jacobi forms, which has the same data is specified by its components, okay? And then they all have integer coefficients, such that they all have integer coefficient. And this 39 is also very interesting. So they are classified by 39 groups on the upper, on the acting on the upper half plane, okay, that define genus 0 quotients on the upper half plane. Hence, what I'm saying is that its fundamental domain is basically a genus 0 Riemann surface. And this gamma can be then correspond to the, is specified or determined by the symmetries of the function you get, okay, in a particular way that I won't get into. So that's very nice that we get a finite set of optimal functions. Okay, so and there's a few properties. So indeed, most of Ramanujan's examples are reproduced in some of the FIs in this list of 39. So including the F0 example we have seen, is which occurs when M is 42. And the second property is that the relation to Moonshine that we have also heard about in this conference. Namely, we have seen that J, the monstrous Moonshine function, is optimal. And indeed, 23 of the 39, which are exactly the 23 with positive coefficients, okay, are exactly the functions of what's called the umbral Moonshine that was discussed by Jeff and John Duncan and myself. So for instance, when you take the function at m equals 2, then the function, the optimal function you have is indeed this function, and which is the star of what's called the M24 Moonshine. So this is 2Q. Apart from the leading term, this encodes the dimension of some M24 modules, okay? So that leads to a very interesting investigation of symmetries of string theory on K3 background, etc. So we see a close connection between like the rare optimal functions and the rare occurrences of Moonshine. And so you might ask, are there more instances like this? And I'll share with you some more recent results. So if we consider, you know, also mock Jacobi forms at weight 2, then optimal, meaning like, again, the components are finite at cusp, is also a problematic definition, because before it has no solution, now it has too many solutions. So one famous example is a function that plays an important role, for instance, in the Vafa-Witten theory on CP2, which is the Hurwitz number function. So this is the Hurwitz class number, and which is actually one of the first, you know, mock modular forms that have been discussed in the modern way. So this function indeed is optimal in the sense that it's finite at all cusps. So too many solutions. So how do we cure this problem to have a, you know, interesting classification problem, just like before in the weight 1 case? So we define the notion of alpha-optimality. So namely, so the functions, they not just have to be finite, but they have to be 0 most of the time and approaching minus alpha for tau going to different kinds of cusps, for instance, I infinity and gamma equivalent, and vanishes otherwise. So you're, you know, it's almost like a cusp form, except where you can have finite value at one cusp that's given. So now we can phrase an interesting classification problem, and let's see what the result here is. So the result here is that by considering such a definition, you can indeed find interesting connections to finite groups. And just because like this is not like we have a priori too many solutions, so now you can have like, you know, connections to not just the exotic sporadic groups, but actually almost any groups. So for instance, take a cyclic group with prime order. So big N is a prime number, okay? So the smallest alpha, which is we take to be a positive integer, such that there exists virtual module. So virtual module, it means like you take representations together with plus and minus sign. So there is a natural Z2 grading, which is natural, for instance, if you count BPS states, because you always count it with a sign in order to have like the desired cancellation. So you have such a module such that, you know, all the trace functions defined as basically the character of such a module graded by two variables are all alpha optimal. And in particular, when G is the identity, then this is just, you know, given by the Hurwitz number times Hurwitz class number function. Then you can show that such an alpha, minimal alpha, is given by the numerator of this thing. And it has nice interpretation in terms of arithmetic geometry that's I'm not going to get into, but here the second example, you can see a nice interpretation showing up. Now, well, that was for any cyclic group of prime order. Now you take, for instance, a material group for M11, now you can show that such alpha is now 2. So, okay, using this, you can actually show it's not really a corollary, but because it requires very non-trivial step. Anyways, consider, you know, negative coefficient, negative number integers that's square free, and you need this funky modular requirement. Then if, you know, this module for M11, well, so contains the representation chi 55, which is M2 irreducible, which is an irreducible representation of the group, okay, that has dimension 55. So anyways, a particular representation. So if, okay, this module contains this piece, then you can actually show that D is not a congruence number. So what is a congruent number? Congruent number is a number, well, sorry, I have some problem with my pen. So a congruent number is, you know, the area of a triangle with, right, like this, and with all the sides being rationals. So if you look at it, it's pretty cool because, I mean, from, you know, you can from the classification of optimal functions, and you connect that to finite group representations, and from there you can connect to completely different problems for instance, this congruent number in arithmetics. Okay, so that's what I want to say about relation between optimality and Moonshine. And I'm now ready to move on to some quantum modular forms and more physical applications. Is there any question, urgent question right now? Okay, so now let's take a closer look at the limit. So for instance, if we have seen, what we have seen is this. So for, you know, let's say Mach theta function, and it blows up at the cusp, but we can subtract in the modular form to cut off singularities and take the radial limit to near a point at x at the rational number, and then you can have a asymptotic expansion near the cusp. And in fact, you can show that this is the same expansion of the shadow. Okay, so that's not easy, that's not difficult to show. So, okay, so what you can see now, is this. Now consider again this co-cycle that's given by the function, namely the limiting behavior of this. And with its modular image subtracted. And this is no longer 0. Right? Instead, this is the same with f check replaced by G star. But since G star is given by an integral, so its modular difference is in fact given by a period integral, and it's easy to compute. And since it's a period integral, we know that it's actually, you know, real analytic in x. So you can take x a little bit away from your rational point and still completely make sense. So that seems to be the natural generalization of the behavior of modular forms near the cusp. So this and other examples led Don Zagier to consider the notion of a quantum modular form. So, which I'll call QMF. So, which is, you know, a function f check on the rational such that the co-cycle function, which is defined as above, is nice. So nice can mean many things. For instance, real analytic is definitely nice. So that's why we say that Mach modular form is an example of quantum modular form. So we have trivial example of modular forms and Mach modular forms. And some other example that we encounter is the what's called the holomorphic Eichler integral, and which is the holomorphic version of, if you want, the G star integral that we have seen. So now, for instance, for integral weight, it's literally such an integral. And it has led to the full theta function, for instance, that you have seen in previous talks. Also, so false theta functions are not Mach modular forms. They are not modular forms. They don't have nice modular properties. However, it satisfies the same condition near the cusp. That's why it also falls under the umbrella of a quantum modular form. Okay. So moreover, G star, the holomorphic Eichler integral, and and the G tilde, the holomorphic one, and G star, the non-holomorphic one. And we know that G star look at the same at the near the cusp as the Mach modular form if they all have the same quantum modular properties. To be more precise, okay, we have seen, let me just repeat it again. This is the same as this, the same limit, and goes like this. Then if this is true, then for the same modular form G, but you now integrated holomorphically instead of non-holomorphically, then you get this expansion, which is a very simple relation. Okay. So a simple example, as I alluded to, is that you take this theta 1 function that we have encountered earlier and take an isolated integral, and what you get is indeed the false theta function. So it's called false because if you take out the sign factor, then it's nothing but the usual modular form. Okay, so it satisfies this condition. So what's really funny is that if you look at where the minus sign is from, it's as if near, at least near the cusp, right? Near this point, this Q point, then there the two are related with a tau to minus tau transformation. So there's also like more concrete ways you can see this, either by, looking at the Eulerian series and then expand it outside the unit disk, or more systematically in terms of Rademacher sum, not Rademacher form. Then this Rademacher sum will define a function both in the lower and the upper half plane, and they're indeed given by, the Mach modular form versus the isolated integral of its shadow. So we will now look at a very nice home for such a very natural home for such a structure, okay, of quantum modular forms. So that's in the context of three-manifold and not invariants, and I'll focus on three-manifold case. So if there's any question, it's also a nice point to raise them. So as we heard also from previous talks, well, given a three-manifold M3, and we'll focus on the SU2 gauge group for now, then we have a topological invariant that's defined on the integers, namely the WRT invariance, which is basically the Chern-Simons partition function. Okay. And as we have also heard briefly from Sergey's talk, in this paper, following earlier papers, they have defined or proposed the following Q-series invariants, or actually a set of them labeled by B, which you know can be thought of as spin C structure or H1. Okay, my comma is a bit long, anyways. So this can be thought of as counting BPS states of a 3D theory, supersymmetric theory, TM3, or doing path integral in the following, background where there's a boundary torus with complex structure tau, and then boundary condition given by this choice of B. And as such, you should have integral coefficients. Okay? And moreover, it's supposed to get related to the WRT invariance by doing two things. The first thing is to take, the limits of tau going to 1 over k of such a function. Okay, so taking the radial limits of this function on the upper plane, and then we have some k independent matrix that plays a role of a change of basis if you want. It has various interpretation, and then we sum over this label B. Okay. So what's especially important for us is this limit. All right. So in this case, well, if we take z hat as our function on the upper half plane, and then take the special elements, namely the S element of S to Z, and look at its, co-cycle. That's x equals 1 over k, as here indicates. Okay.
Sorry, Professor Cheng. Just
Yeah.
a question for clarification.
Yeah.
In the conjecture, the sum is over A, B. B's
Yeah.
are the homology cycles or the spin-C structures, and A's are.
Yeah, you can let both of them to be in the torsion part of
M3.
Yeah.
I see.
Yeah. To the H1. Yeah.
Okay. Thank you.
Yeah. You're welcome.
Yes, question. So,
yeah.
Do you know if there is any relation between the Z hat B and the Habiro series, which I'm not sure you were in the talk, but it's somewhat similar in spirit in that specialization gives rise to the WRT.
Right. So indeed, the story is very, very similar, but Habiro series, they lie in the Habiro ring, so there's equivalent relation. And here you could see that Z hat has to be a very concrete Q series without no ambiguity, because the coefficients actually count BPS stay, so there's no equivalence. But yeah, but they should skip the same results after, yeah. Yeah. So if you want, I would be, I would like to think about Z hat to be sort of the finally pinning down what this Habiro series should be, because it's actually a Q series instead of, yeah.
I see. Okay, thank you.
Okay, so now let's look at the co-cycle, which is basically as before, just the value, the limiting value at near a cusp, and its, modular transformation. Okay, so what we could see here is a structure that this is not gonna give Chern-Simons, and this will then give in the large K limit, in the classical limit, this will give the saddle point contribution from corresponding to different flat connections. And this part is gonna be some perturbative part. So if it's perturbative in 1 over k, then of course we expect it to be nice, continuous, analytic, real analytic, and so on. So that's why we expect Z hat to be quantum modular forms, even though they have no reason to be modular forms a priori. So to quickly summarize, okay, we have Z hat, and we take, let's say, the limiting value. Okay, then we have some other function, Z tilde of k, which should be a quantum modular form. So indeed, you can, in large K, it should look like some trend series of in the complex Chern-Simons. Okay. And then you can again take some sum over some labels that's well understood by now and get the WRT. So that's quantum modularity and why it's natural and necessary in this current context. Okay, so I think I just have time to flash some results that solidifies this physical expectation and shows different structures and interesting structures that's in the story. So assume that M3 is some, subclass containing all ciphered manifolds called plumb manifolds. Then if we restrict it to have 3 exceptional fibers, in the cipher fibration, then in fact you can show that indeed the hat is given by full theta functions in a very restricted and nice form. So this depends on oh, here's the typo. But anyways, a lot of previous work by different people, starting with the observation by Lawrence and Zage on the Poincare sphere. And for general cipher manifolds, so not necessarily 3, you can have arbitrarily high number of exceptional fibers. We have, again, for all the z hats, it's a linear combination of full theta function that we have seen before and the Eichler integral of the other, the weight 1/2 theta function, but also full theta, also theta-like functions and its derivatives. Okay, so the story gets a little bit more intriguing and complicated, and the different types of quantum modularity reflect the different structure of trans series for complex transimers on different types of 3 manifolds. And you can also generalize it to higher rank gauge groups. In fact, all ADE should be fair game. And just very concretely for SU3, then you can show that this is a depth 2 quantum modular form. So, the higher depth quantum modular form is a notion that's very similar to higher depth Mach modular form, which says that now the cocycle doesn't have to be nice and analytic, but the cocycle is, the quantum modular form itself are of lower depth. Okay, so it's a recursive definition, which has nice physical interpretation, in particular in terms of multiple M5 brane interpretation. And a very beautiful story I failed to have time to cover is that there's also a close relation between quantum modular form and the characters of log BOA that Sergey alluded to in his talk. And I messed up the slides a little bit. I should have left some space here. Okay, so here, okay, so I use the space here. So recall that actually the transimers has a very nice transformation if you flip the orientation of the 3 manifolds. Namely, you just flip the sign of the renormalized level. Okay, so because we expect the limits to be like, tau to 1 over tau k, 1 over the level in this case. So it's like you expect the hat of M3 of tau to be the same as, if you flip the orientation, you also flip from lower to upper half plane. But that's pretty bizarre because what is it actually? But fortunately, in the case that we know that on the one side, the answer is given by a full theta function, then which is an Eichler integral of a shadow, some natural Mach theta function. Then, so just, from this number theoretic point of view, it's natural to expect that when you flip the orientation, you actually get a nice Mach theta function. So the conjecture is that indeed, if before flipping, you know for sure that the answer is an Eichler integral of some g, some modular form G, then you expect that after you flip the orientation, the answer is a Mach modular form whose shadow is given by G. Okay, and then you can define it. This is work in progress with a student of mine that, and with some preliminary results already on the archive. That so. Moreover, you can use indefinite theta functions, which appear again and again, and for instance, recently in the context of BPS counting and so on, to define it. And then similarly also should hold for higher depth cases. Okay, so this gets repeated. I apologize for it. So now it's time to conclude. So in the first part of my talk, I discussed the optimal behavior when you go to the cusps, when you go to the boundary. So what does optimal behavior mean, right? So it means that slow growth in coefficients and hence in the physical context, a slow growth in in the number of states. Okay, so in the context of 2D CFT, okay, which is relevant for both Mach and usual modular form, then the next case of small central charge. You can also have a notion of optimality that arises like a sparse, low-lying spectrum, right? Then you get something like QC/24 and some relevance of functions like this. And for instance, that corresponds to the study of, let's say, pure gravity theory and related cousins. And finally, we also see that such a notion of like, specific behavior near the cusps leads you to special modular forms and Mach modular forms that have a rich story relation to finite groups via the so-called Moonshine phenomenon. Okay, so to describe behavior near the cusps, we are naturally led to the definition of, oh my God, my pen is acting up. Sorry. Sometimes it happens, I don't know why. So a quantum modular form, okay? And the context we have seen it is the three-manifold and not invariants, apart from all the above, which also fall into the category of quantum modular forms. Okay, and then whose quantum modularity can be understood via, the complex transassignments, and actually it tells you more than that. And another sort of interesting context it shows up is like that of log VOA, and the fact that you get no more modular forms as characters is of course related to the fact that now you're dealing with the irrational theory. So the modified modularity, namely the quantum modularity, should tell you something about the structure of the representation category of this such a VOA. So there's really a rich story that needs to be, understood and extended. And hopefully one day soon, we will understand the role, the relevance of quantum modular forms in physics, just as we are gaining increasingly a good understanding of the role of Mach modular forms in physics. So that's the end of my talk. Thank you very much for listening.
Let's thank Miranda for a fantastic talk. Are there any questions?
I have a small question. So the class numbers that showed up, the Hurwitz class numbers, they were always for negative fundamental discriminants. There were 4 minus 4 minus L squared, or
Yeah, so indeed it could be like 0 or 1 mod 4. Let me show you. Yeah,
there.
so indeed they're always negative in this case.
And just for so in so in the supersymmetric context, how much supersymmetry does the theory have? Is it n equals 2 or
Yeah.
4 or even higher?
Yeah, 4, 2. Yeah.
2. Okay.
So that's, yeah, the buffer intact.
I have a possible, okay, before I ask, any other questions from Miranda?
Okay, then I have one question. So you explained the results about this optimal choices and allowing the singular behavior, etc. So and you explained the result, but could you explain a little bit more detail how you find the optimal choice and how by some trial and error, or let's see, or do you have a more systematic way, I guess?
Right. So very good. So for instance, in this, weight 1 Mach modular form context is we're
Yes.
very pleased and rather surprised to find a finite list of answers, because a priori the list can be infinite. So historically, such an investigation started when we were looking for Moonshine with Jeff Harvey, who's going to speak in a moment. And there we used a lot of trial and error. So in particular, we used a lot of numerical computations in using Rademacher sums. And then when we prove this result, then there's more systematics and yeah.
And what type of systematics, if you can explain briefly?
Yeah, so so the relation to genus 0 group is pretty crucial. So, so there's a relation to genus 0 hub module. So the optimal functions on the side of weight 0 modular forms, which are close cousins of the J function. So that's pretty crucial. And also just like commonly used in the context of modular forms, the result of Brunier and Funke has been instrumental. But yeah, it took us a huge amount of time.
I see. So it's highly non-trivial. I see. Thank you.
At least non-trivial for me. I don't know. But yeah. But yeah, I forgot to mention that such notion of optimality was also discussed in a paper by Atish and Samir Murthy and Zagir a few years earlier, and they have made the observation that such optimal forms seem to be rare. Also via numerical experiments, but yeah, I think we actually proved that there's finite number of them.
Okay, great, thank you.
I have a question, very naive one. Is there a way one could think of a generalization of quantum modular forms to quantum Siegel modular forms?
I can't see why not, because there's also the notion of a boundary of the moduli space, right? And so, I mean, just in terms of definition, I don't see why not. But in terms of you want to have a definition with interesting examples, then I'm afraid I'm not an expert of Siegel forms enough to see a priori whether you get an empty definition or a definition that's far too general, or like the case of QMF that's defined by Zagier, that seems to be just right to capture the right number of stuff and all interesting stuff. But in terms of definition, I don't see why not.
And would the definition first require a definition of what a Mach-Siegel form is? Because that doesn't exist yet, right?
No, I think I thought there's some recent attempts at it. But I look at reference if I remember correctly. But I don't see it a priori that it's connected a priori. So I explain what the definition of QMF is and how do you actually see that Mach module form is an example of it. But after all, you can define something more general without a priori furnishing already non-trivial example. So in terms of logic, I don't see why one has to depend on the other. But here in the module form case, it seems natural, like and very nice that it generalizes the notion of Mach forms.
And also, if I understood it correctly, did you say that there was some attempt to define a Mach-Siegel form, or?
I thought so. I looked at it. I mean, I'll stick around, but if I found it, I'll just send you the reference.
Oh yes, please. Thank you.
I mean, that's my vague memory, but I need to check if the paper I kind of vaguely recall was indeed doing what I thought it did.
That'd be very useful. So Miranda, thank you very much for the talk again. So let's thank Miranda for the talk.
Thank you very much.
Let me stop recording.